Hi, welcome to Module 4 of Video Lecture 4. In this one, we're going to cover the second rule of differentiation that we're going to talk about in this course, the chain rule. The chain rule is so named, I think, because it takes compound functions and differentiates them by chaining together the derivatives of the individual pieces in the compound function. Before we talk about how to do that, let's remind ourselves what a compound function is. So, if you recall back from lecture 2, we discussed compound functions, function composition, and look kind of like this. We have some h, it's h of x, which is equal to g of f of x. That's a compound function. You take f of x, you plug in your x, whatever you get out of that, you plug into your g, whatever you get out of that is your h of x. So for instance, if f of x were 3x squared and g of x equaled, say, 2x plus 7, then h of x would be the function you would get if you take g, and every time you see an x in g, you plug in f of x there instead. 2 times 3x squared is 6x squared, so we have 6x squared plus 7 is h of x in this case. You can do this to make more complicated functions. So one we've dealt with before would be f of x equals g of x equals x cubed. We can use, so it's just a straight power. How does that work? Well, h of x is equal to f of x cubed, or again, we've just taken the x and g of x and plugged in f of x. That's equal to x cubed cubed, or x to the 9th. So we can compose any function we want in this way. Now, in most cases, you're not going to see polynomials put together in such a way that you really want to compose them. That's not true in all cases, but when you're just composing polynomials as we're doing so far, there's not much reason to use function composition at all. We're using it purely as examples for the chain rule that's coming up. But very quickly, starting in the next video lecture, we're going to deal with actual examples of functions that it's necessary to treat them as composed functions to differentiate them at all. One example of that is an exponential. This is an exponential. We'll see this derivative is easy. It's the easiest one possible. But what about this one? That seems really complicated, but this is precisely the kind of function that we're going to need the chain rule to differentiate. And what we're going to do is call this thing f of x, and g of x is this thing, and therefore g of f of x is what you get when you take g and you plug in f of x wherever the x's are in g of x. So there's an x up here, you plug in x squared plus x there, and that gives you this function. So the key thing to remember here is in all cases of composed functions, you're taking your outer function, and wherever you see an x in the outer function, you're plugging in the inner function. And that's going to be the key to understanding the chain rule coming up. So if you're not clear about any of these parts, look at it again, rewind, look at it again, maybe go back to lecture 2, find the parts about compound functions, watch them again to assure you understand it. Because if you don't get compound functions in general, and they are the trickiest part of, I think, differentiation in this case, you're going to have a real hard time understanding the chain rule. Okay. So when we're done with that, come back, and we're going to go on to looking at the chain rule proper. Okay, now for the chain rule. First, before I actually write the chain rule down, what we're going to do is derive the chain rule, because the components to the derivation are help with the intuition of the chain rule itself. And note, though, for the derivation here, we're going to be hand-waving a little bit. I'll show you when we do it. The goal of this derivation is to get you intuition into the chain rule, not to provide a completely formal definition. Okay. That said, let's begin here. Okay. chain rule. Now, if we want to differentiate the function h, where h equals g of f of x, we can do it in the exact same way we normally do. So, the limit as h goes to 0 of g of f of x plus h minus g of f of x divided by h is the derivative of h. How do we know that? Well, the first term here is h of, so this term here is h of x plus h. H is too many h's, but you get my point. The second term is just h of x. So it's the exact same as the derivative of h of x. Okay. What do we do with this now? Well, what we can do with this is multiply and divide by the same thing, this over here. F of x plus h minus f of x. Now here's where the hand-waving part comes in. You can't multiply and divide by f of x plus h minus f of x if that thing is 0. Right? It's not kosher to multiply and divide by h by 0 over 0. You can't do that. However, let's hand wave past that and just do it anyway, because it helps understanding our intuition behind this thing, behind the chain rule. So let's do that. That gets us the limit of h goes to 0 of g of f of x plus h minus g of f of x divided by that thing we're dividing by, and then multiplied by that thing we're multiplying by, divided by h again, and that should be equivalent as long as that thing in the denominator is not 0. Okay. Now, why do we do that? Well, I hope some of these parts now sort of give you a hint of why we're doing that. Look at this part over here, part on the right in parentheses. The limit of that is a definition of the derivative of f. Now we know that the limit of the product is the product of the limits. We know that from video lecture 2. So we can put the limit through there, and that thing just becomes the derivative of f. So this thing over here is just going to be f prime of x. So I get rid of that stuff. Now that's only useful though if this thing I just bracketed is actually something by itself. To get there, let's make a substitution. U here is going to equal f of x. Z is going to equal f of x plus h minus f of x. With that substitution, that thing in brackets becomes g of u plus z, because u plus z is just f of x plus h, minus g of u divided by z. Now, if we want to include the limit, we can do so, and we should do so. There's no more h here, though, but notice that as h goes to 0 in z, z also goes to 0. So the limit as h goes to 0 is the exact same thing as the limit as z goes to 0. And now that bracketed term becomes this thing down here, this bracketed term, the same thing. What's that bracketed thing? Well, ignoring the fact that the old h has become z, and the old x has become u, this is again just the definition of the derivative of g, but g of u this time. So this thing is going to be g prime of u. So the derivative of the whole thing ends up being g prime of u times f prime of x. Now at this point, you might be wondering, whoa, wait a second. That doesn't seem to help us very much, right? We've gone through and we've converted this thing to g prime of u f prime of x, but now we have a u in there, right? What's the point of that? Well, remember that u is just f of x. There's no difference. So this thing is the exact same, and I'm going to use a new thing for this. It's the exact same, so g prime of u is just g prime of f of x. What that means is we treat g as a function of u, this thing u, right? We differentiate it, as we would any other function. Doesn't matter if it's u or x or anything, it's just a variable. Once we're done with that, we plug in f of x into where u is in that derivative, and that is what gets multiplied by f prime of x. Together, that gives the chain rule h prime of x is equal to g prime of f of x, f prime of x. This is the chain rule. The key thing to remember is that this derivative is accomplished by replacing whatever the f of x in g with a u, taking the derivative, then plugging f of x back in. So for instance, this is our function h. First we make u equal to f of x. We get g of u. We differentiate that with respect to u, ignoring that u is actually f of x. We just differentiate that with respect to u. And we get g prime of u. And we plug back in f of x to get this thing. Right there is the tricky part. Everything else is pretty clear. You can easily find f of x, take a derivative. There's nothing, there's no u's, it's just normal derivative. The tricky part is making sure you take the derivative of g correctly. Okay. To see how to do this, first I'm going to give you some sort of steps to work out, then we're going to go through new examples. So first the steps. Okay, step 1, make u equal to f of x. The tricky part there is identifying what should be f of x. And so far I've just given you f of x, right? But in real life, you'd have a function that might be complicated. You have to identify the different pieces of the compound function. You almost never use this kind of technology for polynomials because you don't really need to when they're just summed together. So we'll see examples of how to identify the f of x in the next module when we deal with exponents. It's often actually much simpler than it would seem. Your goal is to make the whole function simpler, and you can often do that by identifying a piece of the function as f of x, and then g of x the part around it. We'll get to a lot of examples of that in the rest of this lecture. But for now, make u equal to f of x. Step 2 is differentiate g of u, treating u as just a normal variable. Step 3 is differentiate f of x. Step 4 is plug back in f of x into g prime of u to get this. Step 5 is to multiply g prime of f of x times f prime of x. That thing is going to be h prime of x, assuming h is g of f of x. That's it. I'm going to write it up here just to make sure it's clear. Okay. Those are the steps in the chain rule. As you get more familiar with it, these steps will be very clear. For now, though, it'll take some practice to get used to them. So let's give a few examples before we close off this lecture, this module. Okay. First example, we'll do the x cubed one, where f equals g equals x cubed. Okay. Step 1, identify u. Well, they're both x cubed, so we'll make u equal to f of x, which is x cubed. Step 2, compute g prime of u. Now, g of x is just x cubed. That means g of u is just u cubed. That's the important thing to keep in mind. It's the easiest thing to lose track of is that g of u is the same thing as g of x, just replace x's with u's. G of f of x is the same thing as g of x, just replace x's with f of x's. Right? This is the complicated part. It requires some practice, but you'll get it. With practice, you'll get it, and soon it'll be second nature to you to do that. So there's that. What's g prime of u? Well, the derivative of x cubed we saw in the previous module was just 3x squared. So the derivative of g of u is just 3u squared. So that's step 2. Step 3 is the derivative of f of x. well, f of x is also x cubed, so that's just 3x squared. Now step 4, we replace g prime of u and replace u with f of x. So g prime of f of x equals 3 x cubed squared. So you see what we've done here is taken 3u squared, which is g prime of u, and replace u in that with f of x. F of x is x cubed, so x cubed goes in the spot where the u was. So we have 3 x cubed squared. And this thing is 3x to the 6th. And the last step is to multiply that times f prime of x. F prime of x is 3x squared. So we have 3x to the 6th times 3x squared equals 9x to the 8th, which is exactly the same as the derivative of x to the 9th you would get if you just used the power rule and pulled the 9 down and subtracted 1 from the power of x. So that checks out, and that's how you use the chain rule. I'll do a couple more examples quickly. Or 1 or 2 examples, we'll see. So let's try a little different one. Let's try f of x equals x to the 7th. G of x equals 2x plus 2x squared minus x. And look for g of f of x again. So first, u equals x to the 7th. Second, g prime of u equals derivative of 2x squared minus x. Remember, the derivative is a linear operator. That's just a polynomial. So what we'll do is first separate the pieces. Then pull out the constant. And then, see, I went too fast here. These actually should be u's. And good for you if you caught that at home. These all should be u's. And again, I didn't just delete that from the video because it's good to know that no matter how many times you do this, it's still possible to make mistakes. Particularly on the fly. So be very careful and make sure g of u is a function of u. That's important because when you go back to put things back in again, you want to make sure that you're putting the right thing back in again. You want to put f of x where the u is. If everything's x, it gets confusing. Okay. So these are all u's. The derivative of u squared is 2u. So that first term is 4u. The derivative of u is 1. So that's 1. There's g prime of u. The next step is derivative of f. Here we have x's, so it's easier. Use the power rule here. Pull down the 7. 7 minus 1 is 6. And you get that. That's it. Now, replace f of x into g prime of u. So g prime of f of x equals 4x to the 7th minus 1. Because I put where the u was, I put an f of x in there. And finally multiply to get 28x to the 13th minus 7x to the 6th. Again, we can check because these are polynomials. G of f of x is equal to 2x to the 7th squared minus x to the 7th equals equals 2x to the 14th minus x to the 7th. Power rule says you pull down a 14 on the first one to get 28x to the 13th. And you pull down a 7 to get 7x to the 6th. So you have 28x to the 13th minus 7x to the 6th, the exact same as before. So we can do it either way you want, but the chain rule works out correctly. The last example will be a very brief one to give a prelude to the next section. Let's say I wanted to take the derivative of e to the x squared, as we'll do next time. What should we do? Well, we can identify f of x equal x squared and g of x equals e to the x. well, then we can use it as a compound function. U would equal x squared. G prime of u would equal the derivative of e to the u. This we have to wait to next time to figure out what it is. Little hint, little preview, it's going to be this. That's why exponentials are awesome. F of x derivative is going to be just 2x. So g prime of f of x is going to be the original function back again. You just plug in to u x squared, and then multiply together. You get the whole derivative is 2x e to the x squared. And that's how you can differentiate compound functions. And unlike the case of the polynomials, you're not going to get this derivative by just multiplying up together and plugging them all in ahead of time to make h just a simple function. It's just not a simple function. It's a compound function fundamentally, and you need a chain rule to differentiate it. And that's why we end up using the chain rule. So thank you very much. And the next one will actually go and derive this derivative right there. Thank you very much.